Good morning, everyone. So, welcome to my YouTube channel. So, today we are going to see 16 lecture on Riemann integration. Let's start today's session. So, today we are going to prove an important result. If a function is bounded on a closed interval and have finite numbers of points of discontinuities, then such type of functions are always Riemann integrable. Okay. So, this is theorem actually. Let F closed interval AB to R be a bounded function. Bounded function. If F has if F has finite number of points of discontinuities on closed interval AB, then F is Riemann integrable over closed interval it means F belongs to RAB. Okay. Let's see its proof. So you write F has at most finite numbers of points of discontinuity. At most finite numbers of points of discontinuities on closed interval AB, then F is Riemann integrable over closed interval AB. Okay. Let's see its proof. Let W1, W2, Wm be points of discontinuity of F on closed interval AB. Okay. Now you see that we have closed interval AB. close interval AB, and there are W1, W2, okay, like that. WM minus 1 will be there, and WM will be there, okay, and so on, okay. So these are the discontinuities of W1, W2, W3, WM, okay. Now we can enclose their discontinuities. We can enclose their discontinuities in a subintervals Y1. I can Y1, Z1. This I can enclose in between Y2, Z2. Okay. This I enclose in Ym minus 1, Zm minus 1. And this can be enclosed Ym, Zm. Okay. So given let epsilon greater than 0, let epsilon greater than 0, so we can find choose subintervals Y1, Z1, Y2, Z2, and so on, Ym, Zm, okay, with Y1, sorry, W1 is in this interval, W1 is in Y1, Z1, W2 in Y2, Z2, okay, and so on, Wm in Ym, Zm, and the gap between the difference between Zj minus Ym, Yj, Yj is less than m minus m, okay, into, sorry, I should take here L. So I should take here L, okay, because m denotes, I am taking L here. L minus 1, L minus 1. Okay. This is L, this is L, this is L. Okay, so this is such that this is less than epsilon by L times epsilon by 2 epsilon by this is less than epsilon upon 2L. Okay, less than equal to 4 I goes to 1, 2, 3 up to L. Okay, note here. I should write this here. Okay, epsilon upon 2 L M minus M. Okay, you add 1 plus here. Okay, because capital M and small m can be equal also. Okay, so I should write here in a proper manner that it is 2L capital M minus M plus 1. Okay, it will be better. Okay, now this one. Okay, then what will happen? Then summation, this is J. Okay, J goes to 112. J goes to 1 to L. Okay, Mi Mj minus small mj and difference of Zj minus Yj. What will be this? What will be this? This is always less than equal to summation J goes to 1 to L. The supremum of F over interval Yj, Zj will be less than supremum of F over all closed interval AB. Okay, so I wrote M here, and this infimum on subinterval will be less than will be greater than infimum over closed interval AB of F. So this is Zj minus Yj. So what is this? This is nothing but 1 goes to L M. Put the value of this. This will be greater than equal to epsilon upon 2L M minus M plus 1. Okay. So I can take this outside. Okay. So this is M minus M upon 2L M minus M plus 1. So this is epsilon I can take outside. This is J goes to 1 to L. Okay. 1. So I am taking 1. I am adding 1 L times. Okay, so it will be L. So it is L. So L is cancelled out. Okay, but M minus M is greater than equal to 0, and which is less than M minus M plus 1. Okay, so this will be what? So M minus M upon M minus M plus 1. This is epsilon by 2. Okay, so this will be less than equal to 1. So this will be less than equal to 1. So what is this? Epsilon by 2. Okay, so this implies so this implies summation J goes to 1 to L M I minus M I small m I Z J minus Y J Y J. This is less than equal to epsilon by 2. Let's say this equation number 1. Let's say this equation 1. Okay. Let's say this equation 1. Okay. Okay. Now, we have this interval. Observe that. Sorry. Now, we have this interval A, Y1. Okay. Okay. Then this is Y1, Z1. And then this is Y2, Z2. Okay. And this is then YL, ZL. YL, ZL. And next interval is ZLB. Okay. So these intervals are settled down. These are settled down. Okay. Now we have to focus on this one and this one. Okay. So this one and this one we have to focus on. Okay. Okay. Now take now because F has a finite numbers of discontinuities, we have dealt with these discontinuities by enclosing this Wj Wj discontinuity by the subinterval Yj Zk. Okay. Now, since, but on this subinterval, since f is continuous on A1, sorry, is continuous on the closed interval AY1 AY1 and ZLB, we get, because we know that if function is continuous, it is Riemann integrable also. We get f is Riemann integrable over AY1 and ZLB. Okay. Now choose partitions P1 of AY1 and P2 of ZLB such that U P1F minus L P1F is strictly less than epsilon by 4. Okay. And U P2F minus L P2F less than epsilon by 4. Okay. So let's say it's equation number 2. Okay. Okay. Now put now let's say Q1 is Y1 Z1. Okay. Partition of Y1 Z1. Okay. Q2 Y2 Z2. Partition of Y2 Z2. Okay. So and so on. And so on. Okay. QN is equal to YL that is less than ZL. Partition of YL ZL. Okay. Okay. Then what happens actually? Then what is U QJ F is equal to minus So summation so this is minus L Q J F. I am taking summation of this. Summation J goes to 1 to L. That is nothing but summation J goes to 1 to L M J minus small j. This is Z J minus Yj. But from equation number 2, it is less than epsilon from 2. Okay. So let's say it equation number 3. So what we have? We have this one. So we have summation J goes to 1 to L U Q J F minus L Q J F, that is less than equal to epsilon by 2. So this is equation number 3, you say. Okay. Now consider a partition. So put P is equal to P1 union Q1 union Q2 union QL union P2. Okay. So this is partition of so put this one, then so P is then P is partition of, so this implies P is partition of closed interval A B. Then next, what is this UPF minus LPF is equal to, what is this? This is nothing but UP P1F, okay, minus L P1F plus summation J goes to 1 to L U Q J F minus L Q J F, okay, plus U P2F minus L P2F, okay. This is this, okay. But this is strictly less than by equation 4. Next, by equations 2 and 3, we get this is less than, strictly less than epsilon by 4, and this is less than equal to, but here strictly sign, so it will remain strictly sign, and this is again by equation 2 strictly less than epsilon by 4. So what is this? This then, this is nothing but epsilon. So this implies given any epsilon greater than 0, there exists P, a partition of closed interval AB such that UPF minus LPF is less than epsilon. Okay. So what does it mean? It means that once you have a part given any epsilon greater than 0, once you have a partition of closed interval AB such that UPF minus LPF is less than epsilon, then such functions are Riemann integrable. You can see either lecture 8 or 9, we have discussed this theorem where given any epsilon greater than 0, if there exists a partition satisfying this, then function is Riemann integral. So what does it mean of this? This means that f belongs R in it. It means f is Riemann integral. Okay. So if a function has a finite, at most finite numbers of discontinuities, okay, then such functions are Riemann integral, provided the function is bounded. Okay. So example this, you see the example this. Example 1. If fx is equal to sin x upon x, we are taking if x belongs to open 0, 1 close, and it is 0 if x is equal to 0. Riemann integrable over close interval 0, 1. Solution. Okay, let's check it whether this is Riemann integrable or not. We will say either it is no or yes later. First, let me check first. We will check it first whether it is Riemann integrable or not. Accordingly, we write yes or no. Okay. So what is the function? Function is fx is equal to x sin x upon x if x belongs to open 0, 1 close, and 0 if x is equal to 0. Okay. Okay. Sin x upon x is continuous on 0, 1. Okay. So this implies f is continuous on open 0, 1 close interval. Okay. Now, what is the limit of function? Now we have to check whether f is continuous at 0 or not. Limit f stands to 0 plus from, it means limit from right. It is nothing but sin x upon x. That is 1, but it is not equal to 0. That is value of f at 0. So this implies f is not continuous at 0. It means f is discontinuous at 0. Okay. So f is continuous everywhere except 0. It means f has finite numbers of discontinuities, that is number of discontinuities is 1. F has only one discontinuity, that is x is equal to 0. Okay. And Otherwise, it is continuous everywhere. Everywhere. So it has, so this implies F has only, F has F has F has at most finite, because number of discontinuities is 1, has at most finite numbers of discontinuity. Okay. So this implies by theorem F is Riemann integrable over closed interval 0, 1. Okay. So this is done. So F is Riemann integrable over closed interval 0, 1. Okay. So answer is yes. Okay. Answer is yes. So we are done. Okay. Now move to next question. Example 2. If fx is equal to greatest integer function Riemann, or you can say ceiling floor function. This is floor function, or you can say greatest integer function Riemann integrable over closed interval 0, 6. Okay. Solution. So what is f? We have to take this function. We have to take this function on closed interval 0, 6. Okay. On 6, 0, 6. Then what is this function? So write this function. What is this function? So when you are taking your value from closed interval open, x belongs to, then this function is nothing but 0. And if you are taking x belongs to 1 to open, then this value is 1. And if you are taking this value, it is 2. Okay. And if you are taking x belongs to 3, 4 open, this value is 3. Okay. And it is 4 if you are taking value x belongs to, and it is 5 if x belongs to 5. Okay. 6 open. Okay. And it is 6 if x is 6. Okay. So what is the graph of this function? Let's draw the graph of this function. This is 1, this is 2, this is 3, 4, 5, 6. This is 0, 1, 2, 3, 4, 5, 6. So what is the graph in this? This is this. And 1 to 2 it is, okay. And 2 to 3 it is 2. Okay. And 3 to 4 it is 3. Okay. 4 to 5 it is, okay, 4. And 5 to 6, 5 to 6 open interval. 6 is not here. 5 close interval, 5 to 6 open. At 6 it is 6. Okay. So how many points are discontinuities? X is equal to 1, X is equal to 2, 3. So points of discontinuity are at 1 it is discontinuous, at 2 it is discontinuous, 3, 4, 5, okay, at 6. So points of discontinuity are points of discontinuity of F are X is equal to 1, 2, 3, 4, 5. Five and 6, okay. So 6. So what does it mean? It means these are the only finite numbers of discontinuities. Rest, the domain F is continuous. So this implies F has only 6 discontinuities. Has only 6 points of discontinuity. So by theorem, so this implies by, otherwise F has only finite numbers of discontinuity. It has 6 points of discontinuity. So this implies F has at most finite number of discontinuities. So this implies except, so F has finite numbers of discontinuities, otherwise it is continuous everywhere. Otherwise it is continuous every pair on closed interval. So it is discontinuity and it is discontinuous only 6 points. Otherwise, on the remaining points, it is continuous everywhere on closed interval. Okay. So by theorem, F is Riemann. Sorry, it is 6 here. Riemann integrable over close interval 0, 6. So it is 6 here. Okay. It has 6 here. On close interval 6, F has only 6 discontinuities. Okay. Okay. It means it has only finite numbers of discontinuities. Therefore, F is Riemann integral by theorem, which I have done on the top. Okay. So today's lecture up to this. So we have to write here yes. Okay. Our answer is yes. Okay. Okay. So today's lecture up to this. If you have any problem related to this, you can comment on my YouTube channel. Like, share, comment, and subscribe my YouTube channel. Thank you very much for today's lecture. We will see you in next lecture.